let's move on to the next talk, and it's by Professor Sriram Ramaswamy from IISc Bangalore, and the topic is superdiffusion and condensation without attraction in swimmer suspensions.
Thank you very much for asking me to speak. This is the title. This is work done by my former student, Dr. Chatterjee, who was at TIFR Hyderabad and is now at Leipzig, and we benefited a lot from discussions with Vijay at ICTS and Jain. First of all, of course, it's an honor to talk at an event celebrating the life and achievements of these two wonderful guys. I don't think they're 70. I mean, Mustansir still looks like that. And this is 1993, Deepak, and this is now. I don't see any difference. It's been wonderful working with them, and it's been wonderful in particular, collaborating with Mustansir has been one of the most enjoyable bits of physics I did. So happy 70th and many more. Okay, I'll tell you quickly about active matter. I'll give you an example of the system I'm talking about. First one swimmer and then their collective behavior, and I'll summarize. So my interest is in the collective behavior of particles that are individually powered, self-propelled, or motorized in some way. They are perpetually given some free energy which they turn to movement, and this is one of the more exciting areas of statistical mechanics today. So the particular kind of active particles I'm going to be telling you about are swimmers. So the ambient fluid is really important. If you have one object swimming like this guy, it pulls in fluid like that and ejects it in the two perpendicular directions. If you have something swimming like this, the flow is like this, but with all the signs changed. If you have one such swimmer, the flow field decays quite slowly with distance as 1 over r squared. It's parameterized by the strength of this dipolar force density, which you can think of as the product of a thrust and a length, which could be the stroke or the size or something. Mu is the viscosity. It is anisotropic, and this particular anisotropy you will recognize as something which, if you allow an isotropic averaging, will become 0. The question is, you can see the flow is long range. So if you have many swimmers, can this lead to singularly enhanced mixing, faster than diffusive? Also, if you have many swimmers, can they somehow draw each other in at long distances and condense? If you have an aligned state of these swimmers, an initially aligned state, let's say they have some interactions which make them form a uniaxial liquid crystal when they are dead. When you switch on their swimming activity, what we showed many years ago with Aditi, is that the aligned state simply doesn't persist. There's a growth rate which is proportional to the strength of the forcing divided by the viscosity, which we'll call 1 over tau. And there is a length scale L, which is given by the ratio of whatever liquid crystal elastic constant results from their interactions, we'll call that K, to this parameter with units of stress that I defined here. So there's a length scale xi and a time scale tau. And basically what happens is the aligned state dissolves into a zero Reynolds number spatial temporally chaotic state called active turbulence. And because this state is isotropized, this effect effectively is cut off on time scales bigger than tau. So you get an enhanced diffusion, but a little calculation will show that enhancement is not singular. The enhancement can be calculated in a field theory. You write down a continuity equation for the concentration. You write down an inertia-less equation for the hydrodynamic velocity field, driven by the forcing that each swimmer produces in the fluid. That forcing in the state called active turbulence has a finite correlation length and decays in a finite time. And if you calculate the normalized diffusivity through advection, through this little diagram, you find that because the velocity field, thanks to this rapid decay of the stress, decays with a time scale tau, the diffusivity enhancement is singular only in 2 dimensions, that only logarithmically, and is finite in 3 dimensions. Ultimately, because the decay is not dominated by the conservation law on particles, but by the finite time scale on which the local aligned stress disorients. So the question is, if instead you disperse these swimmers in a medium with which is permanently endowed with anisotropy like this, then the question is, so imagine you've got a bunch of things swimming in a stiff liquid crystal. So then these flow fields should somehow be able to conspire. So what you have is now you've got a bunch of swimmers, you've got a medium anisotropy. The swimmers can swim up and down, they flip frequently, we'll ignore that polarity, we assume they tumble, but they're always aligned with the axis. And of course, they can diffuse laterally as well. So they're moving through this medium, always keeping their axis on average aligned with the imposed axis. If you put in numbers for a system that people have studied, which is Bacillus subtilis, in a class of chromonic liquid crystals, chromonic means made of a certain asthma medicine, it actually turns out. Then the length scale above which the system would disorient is 100 microns. You can probably push this by another factor of 10 by playing with parameters for this concentration. So there exist experimental regimes where it's valid to test this idea of swimmers in a permanently anisotropic medium. So then, in these systems, what happens is the flow is not driven by changes in the orientation, which is basically fixed. It's driven by variations in the concentration. This is a regime that has not been studied in active suspensions. And the hydrodynamic equations for this system look rather like the ones I wrote down a few minutes ago. You've got advection and diffusion and noise. You've got hydrodynamic velocity forced by the active stress. The active stress now has a permanent alignment, and therefore the important variations in the active stress come from spatial variations of the concentration. And what you get, therefore, if you just put in this concentration, this expression here, is that spatial variations in the concentration give rise to flow. The concentration almost acts like a pressure field. This means that the velocity field is being forced by a conserved concentration field. The result is that this nonlinearity here turns out to be relevant in dimensions below 4. So in 3 dimensions in particular, it's strongly relevant. And you can work out, you can calculate the normalized diffusivity. You can do it much quicker than the diagram I showed you. You can just say, imagine you've got a bunch of independent concentration fluctuations, which I'll justify afterwards. Each one will give rise to a flow field which goes as 1 over L to the d minus 1 of but with a direction that could be this way or that way. You square and add these, that's 1 over L to the d minus. Square and add these means it's 1 over L to the d minus 1 squared times the volume, which is L to the d, which gives you 1 over L to the d minus 2. The resulting time scale is length scale divided by this RMS velocity scale, and that goes as L to the d by 2. This, of course, is faster than diffusion only in dimensions below 4. Above 4, it's unimportant diffusion dominance. So what this says, I'll give you a quick and dirty argument for why a bunch of independent swimmers keeping their axes aligned will give you super diffusion. Z is 3 halves in D equals 2. You can improve this by a one-loop self-consistent calculation in the style of Chatterjee's treatment of KPZ. You can check that this approach is okay for a system whose bare noise and bare diffusivity stand in a fluctuation dissipation relation. For that system, you can show that the assumption of a structureless concentration field is justified. And again, we'll get Z equals to DO2. So I've shown you, let me now show you essentially my last but 1 slide, last but 2 slides. There is one feature of activity and anisotropy that I missed, which is actually that there is one more piece to the current. And that piece to the current is the following. If locally I happen to have a velocity profile that varies like this, that will produce a distortion in the orientation of the swimmers, which will look like this. That will give a local polarity. And these swimmers, even if they're flipping rapidly, will now have a transport this way. So local second derivatives of velocity give you a particle current. That particle current now you need to include in this field theory. Okay? If you do that, you can then work out. So if you take this expression for the current, plug it in here, you will find that there's a new term in the concentration equation whose effects you work out in the following way. Concentration fluctuation gives rise to velocity field. Velocity field enters here in the form of an expression that's governed by the concentration. The net effect, as it turns out, this term contributes precisely at diffusion order, but anisotropically. So what you find is that if the activity is large enough, you end up getting a diffusivity that vanishes at in a cone of angles above and below along the vertical direction. Okay, and this is a completely active and completely hydrodynamic mechanism for condensation. Condensation in the sense that diffusivity changes sign. We don't know what the phase separated state looks like. We don't know what the critical point looks like. And we know that hydrodynamic interaction is strongly relevant at this critical point.
Two more minutes.
Yeah, I'm actually essentially done. So that is my story. I showed you that active particles in an anisotropic fluid super diffuse. The calculation that went into showing that was somewhat simplified in the sense that it was based on a purely isotropic scaling ansatz. We don't know if this is superseded by something even stronger, if there's a strong coupling fixed point, that we don't know. I showed you a purely hydrodynamic route to condensation. I didn't say that if I take this second part of the story, active condensation, and replace the bulk three-dimensional fluid by a layer of fluid confined between two plates, the mechanism still goes through, you still get an active mechanism that gives rise to a change in sign of diffusivity and hence condensation. We don't know what the nature of the phase transition is or the phase separated state. There are experimental systems, either swimmers dispersed in liquid crystals or swimmers aligned by polarized light fields, which should be good places to test these ideas. And that's the end. Again, happy 70th, Mustan Sir and Deepak once again. I'm happy to take questions.
Yeah, thank you for your illuminating talk. The floor is open for question. Satya Majumdar?
Shall I stop sharing?
Hi, Sriram. So, can you hear me? Yeah. No, I was just wondering, what is the sort of velocity correlation function in space or time looks like?
Okay, so
velocity or concentration, whatever. I mean, they are coupled, I suppose. I mean,
yeah, the point is the velocity correlation function. Hang on, actually, I'll have to look at my slides to remind me what they look like. First of all, in the so-called active turbulence state, which is statistically isotropic, there, even though velocity correlations decay rapidly in time, they decay slowly in space. So the equal time velocity correlations in active turbulence are 1 over r in 3 dimensions.
I see. Okay.
Here, let's see. I guess here too, to the extent that the concentration fluctuations are structureless, they will still decay as 1 over r, but they'll decay non-trivially in space, in time, I'm sorry.
In time, I see.
Because you can see there's a grad phi that goes to the del squared u. So u is like 1 over grad on phi.
Right.
So the equal time UU correlators, I guess, will be, yeah, like 1 over q squared times the equal time concentration.
Okay, thanks. Yeah.
So I had a question.
Yeah.
For the single swimmer, you had shown that the velocity field is purely radial.
Yeah, so that's a weird property of an ideal force dipole. If you put in two force monopoles, hang on, let me just share. I don't have the picture of the two force monopoles. Let me start sharing again. So just a second. Excuse me, I'm doing it. Yeah, so for an ideal point force dipole, you get this rather odd field. It's a bit weird. What you should do instead is have two slightly displaced fields. Then you will find that there are 4 lobes instead.
But there is no theta derivative of the potential.
No theta derivative of the potential?
If there is a scalar potential whose derivatives give you this field.
But this is not going to be potential flow. Okay. I'm pretty sure this velocity field will have a curl.
Okay. I will understand it later.
Yeah. So this isn't potential flow.
Mustansir Barma?
Yeah, Sriram, so you're associating condensation with zero diffusion constant. Can you just elaborate and explain why?
The idea just means that if the diffusivity goes negative, then inhomogeneities in the concentration will not dissolve, but will instead build up in certain directions.
Okay.
To that extent, it is diffusivity. What I can say with slightly greater confidence is that from the stable side, if you approach this point, you will start to see, if there's noise in the problem, you will start to see enhanced concentration fluctuations on a cone of directions, on a forward and backward cone of directions in Fourier space, right? Because static structure factor is like a noise strength divided by relaxation rate. Both are order q squared, but now the diffusivity will decrease. So the magnitude of concentration fluctuations in those directions will start to increase. So that is what I can say with full honesty. To absolutely declare that it really is concentration, I need to show phase separation.